Hello again, class. This is Mr. Liao, and these are new topics for the 2020 AP Statistics exam. These are not in our textbook. I am throwing them in there now because I didn't get a chance to go through them in class earlier. So I've created a set of notes for you, so all you have to do is read along. There are some multiple choice questions that I pulled from the AP Classroom that you can use to see how these concepts work. So the first topic we're going to be looking at are mosaic plots, and then we're going to move on to sampling distributions between the difference in a sample mean, and a sample proportions. So let's start with mosaic plots. So to use a mosaic plot, we're going to use a set of data. This is the Titanic data that we used all the way back in chapter 3 or 4. I don't remember. It's a two-way table. Again, a two-way table describes two categorical variables. So to refresh your memory, here we have the class of travel on the Titanic, and these are for adults. And then we have survival status, whether they survived or they died when the Titanic sank back in 1912. So to graph categorical data, we learned two main ways to do it. We learned how to do a bar chart. We learned how to do a pie graph. And even with separate variables, you can do segmented bar charts or back-to-back bar charts where you can see how the variables stack up next to each other. Today, we're going to learn a new plot called a mosaic plot. And a mosaic plot is helpful because it allows you to easily graph two variables, categorical variables at the same time. So whenever you're doing categorical data, you need to graph the different values for each variable and the count or percentage of individuals who fall into each category. And generally speaking, it's better to use proportions or percentages than actual counts, because with actual counts, if you just use numbers, you don't really get an idea of what the proportions are or what the relative standings are. So generally speaking, you're going to want to use percentages or proportions instead of just raw numbers. So there are two mosaic plots for these set of data. You have this one, which is conditional frequency by survival status. The mosaic plot on the right of your notes paper is conditional frequency by class of travel. So this plot refers to the table that you have on the left side of your paper. So what you're going to look for is both categorical variables. One variable is on the horizontal axis, in this case survival status. That's the one you're conditioned on, and class of travel in this case is on the y-axis. So the way you would read this is a couple things. First of all, let's look at the people that died. If you look at the table, you will see of those that died, 0.160 were in first class. So what this means is this is 0.160 high. Okay, so you can see how high this box is. The green graph tells you that of the people that died, 0.218 were second class passengers. So the height of this box is 0.218. And then finally, the height of the blue box tells you that of those who died, 0.622 were in third class. So that represents the height of each box. So the height is 0.622. Notice that all the heights add up to 1. So that's the first thing you want to notice. And the same thing with survival. The height of the first box is 0.446. The height of the green box is 0.213. The height of the blue box is 0.34, telling you that of those that survived, most of them were in first class. Now, the other thing you want to read is horizontally. Horizontally, you're going to look at basically the conditional frequency by class of travel. So if you take a look at the graph on the right, you'll see that 63.4% or 0.634 people died. So the width of this, assuming the width of this is 1, is 0.634. The width of the survival group is 0.366. So what the width of each column tells you is the proportion of those in each category. So of those who died, of those passengers, 63.4% or 0.634 died and 0.366 survived. So you notice how it gives you conditional frequency, but it also gives you a relative standing of what the other variable is in terms of how it's broken down. Now we look at a survival by class. Now we have 3 classes of travel, so we're basically looking at the conditional frequency by class. So among the first class passengers, you see that 0.618 survives, so that's this top box, and that represents the height of this blue box, which means the height of the red box tells you the percentage of people in first class that did not survive, those that died. That's 0.382. And you can do the same thing with second class. So of those in second class, 0.64 died. So this is 0.64. This is 0.36. 36% of people in second class survived. And in third class, 0.759 died and 241 survived. So again, the heights of the boxes tell you within each class what proportion survived or died. And just like before, the width of the boxes tells you what proportion of passengers were in each class of travel. So in the first class of travel, you see, based on this graph, this is a width of 0.264 left to right. This is a width of 0.216, and this last one is a width of 0.520. So the mosaic plot is a really neat plot to look at because it gives you the breakdown by each variable. One variable, the conditional variable, you can see the breakdown within each class, but it also breaks down the other categorical variable in terms of what proportion of people or subjects fall into each group. The next topic is the sampling distributions for the difference in sample means and sample proportions. These formulas are going to look familiar because we've used them in two sample procedures for difference in P1 minus P2 and mu1 minus mu2. But this is going to be a sampling distribution. This is new to the AP syllabus. It should make sense. So let's review what a sampling distribution is. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So remember, all possible samples of the same size from the same population, and that it's about a statistic. So it could be x bar or p hat or p1 hat minus p2 hat or x bar 1 minus x bar 2. Always a sampling distribution of a statistic. So let's suppose you wanted to know what proportion of students support increased gun control at our school. Instead of conducting a census, you take a random sample of 100 students and use it to estimate the proportion of all students that favor increased gun control. The sampling distribution of the statistic p hat is what you would get if you took every possible 100 student sample at our school, plotted the p hat for each of those samples into a single distribution. With that distribution, we can calculate the center of all those p hats, the spread of all those p hats, and the shape for the distribution of all those p hats. So this is the stuff that we learned in chapter 9. Now, when we're looking at the difference of two statistics, you are going to apply the rules we learned in chapter 7, which is combining random variables, specifically combining independent random variables to obtain these formulas. So the difference in the means of two random variables is found by subtracting the parameter of one random variable from the other. So it could be P1 minus P2 or mu1 minus mu2. Those are the difference in the means. For the standard deviations, if you remember from chapter 7, to find the standard deviation of a difference of two random variables, you have to add the variances together and take the square root of the sum of those variances for each random variable. Now for this formula, you need to have independent random samples or independent random groups created by random assignment from an experiment. So this is the summary for p hat. This is something we learned in chapter 9. The mu of p hat is p. Sigma of p hat is the square root of p times 1 minus p over n. Now the conditions or the rules of thumb, you need a random sample. You need to have a population that's at least 10 times the size of the sample. That's n, big N greater than or equal to 10 little n. And to use the normal approximation for proportions, np and n1 minus p both have to be at least 10. Now for the sampling distribution of P1 hat minus P2 hat, it's going to be very similar. The mean of P1 hat minus P2 hat is the difference in the parameters. In other words, P1 minus P2. Now the standard deviation is the sum of the variances with the square root taken of that sum. So if you remember, sigma of P hat was P times 1 minus P over N. So if you to square that, you would basically get each of these things separately. Now you're going to add those variances together and take the square root, and that gets you the sigma of P1 hat minus P2 hat. Now these formulas will be on the formula sheet. I'll show you that in a bit. Now again, the conditions, random samples. Both samples have to be random, or we have random assignment. Sigma, the population of both groups has to be at least 10 times the size of the sample of both groups. Again, these should be very familiar conditions. Finally, to use the normal approximation, N1 P1, N11 minus P1, N2 P2, and N21 minus P2 all have to be at least 10. Very similar to the conditions when we did the two sample z-test or z-interval for P1 minus P2. Exactly the same conditions. So let's use some of the examples from the multiple choice that we saw. For two populations of rabbits R and S, the proportions of rabbits with white markings on their fur are given as PR and PS respectively. Suppose that independent random samples of 50 rabbits from R and 100 rabbits from S are selected. Let PR hat be the sample proportion of rabbits with white markings from R, and let PS hat be the sample proportion of rabbits with white markings from S. What is the standard deviation of the sampling distribution of PR hat minus PS hat? So here are the choices. Remember, you are taking the variance for each random variable, you are going to add them together and take the square root of that sum. And that's going to be choice D. So you're not using P hat R P hat S. You don't know what P R hat P S hat are. You're using a sampling distribution where you're given the population proportions for both R and S. So we're going to choose D because it has each proportion for each population as well as the sample size in the denominator. So PR1 minus PR over 50 plus PS1 minus PS over 100. A is wrong because it's looking at means. B is wrong because it adds the variances but doesn't take the square root. C is wrong because the sample sizes are switched, but also you're using sample proportions and you shouldn't do that when you're calculating the statistics for a sampling distribution. E is wrong because again, you don't use PR hat or PS hat, you're using PR and PS. Number 2, a study reported that finger rings increase the growth of bacteria on healthcare workers' hands. Research suggests that 31% of healthcare workers who wear rings have bacteria on one or both hands, and 27% of healthcare workers without rings have bacteria on one or both hands. Suppose that independent random samples of 100 healthcare workers wearing rings and 100 healthcare workers not wearing rings are selected. What is the standard deviation of the sampling distribution of the difference in the sample proportions? In this case, wear rings minus does not wear rings, of healthcare workers having bacteria on one or both hands. Okay, so we can eliminate A right away because it's looking at the difference in proportions. We're looking for the standard deviation. So we're going to do the square root of P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. Thus the answer is C. It's the only one that has P1 as 0.31 and P2 as 0.27. It's got 1 minus each proportion and you're dividing by the sample size. Notice you are adding the variances and taking the square root of the sum. D is wrong because you don't square each one or add the standard deviations, you add the variances, take the square root. E is wrong because it doesn't have the second group. B is wrong because you add the variances, but you don't take the square root to find the standard deviation. B is actually the variance of the sampling distribution for the differences. Number 3, in one city, 75% of residents report that they regularly recycle. In a second city, 90% of residents report that they regularly recycle. Simple random samples of 75 residents are selected from each city. Which of the following statements is correct about the approximate normality of the sampling distribution of the difference in sample proportions of residents who report that they regularly recycle? So we know that P1 is 0.75. We know the sample size for group 1 is 75. P2 is 0.9. N2 is 75. So to find normality, you need to check the normal condition for all of them. N1, P1, N1, 1 minus P1, and so on. So N1, P1 is okay. N1, 1 minus P1 is okay. N2, P2 is okay. But N2, 1 minus P2 is 75 times 0.1, which is only 7.5. I forgot to write down the 75 times 0.1, so I'll put that here on the side. 75 times 1 minus P2, which is 0.1. So that is not at least 10. Since that is not at least 10, the sample size for the second city is not big enough because it doesn't meet the minimum of 10. So looking at the choices again, we want to show that the sample size is big enough for the first city, but not big enough for the second city, which means the answer is B. Now the sampling distribution for X bar. Mu of X bar is mu, this is for one sample. Sigma of X bar is sigma over the square root of n. Again, you need a random sample. The population has to be at least 10 times the size of the sample. And to find the shape to be approximately normal, you have two ways. One is that the population is normal or given to be approximately normal. And the other way is that your sample size is at least 30 so that you can use CLT to approximate normality. Now for the sampling distribution of X bar 1 minus X bar 2, the mu of X bar 1 minus X bar 2 is just the difference in the population means, mu 1 minus mu 2. For the standard deviation, again, you will add the variances together, take the square root of that sum. So since each standard deviation is sigma over the square root of n, each variance is sigma squared over n. So sigma 1 squared over n1 plus sigma 2 squared over n2 is the variance. Take the square root of that sum to get the standard deviation of the difference. Again, you need two independent random samples or groups. For independence, you need to show that both populations are at least 10 times their respective sample sizes. And to use the normal approximation, you need to show that for both groups, either the populations are normally or approximately normally distributed, or your sample size is at least 30 to allow you to use CLT to approximate normality. So you can find either combination. One can be CLT, the other one can be normal distribution of the population, whatever allows you to find that both populations satisfy the normal condition. Number one, for a weekly town council meeting in a certain town, the distribution of the duration of the meeting is approximately normal with a mean of 53 minutes and a standard deviation of 2.5 minutes. For a weekly arts council meeting in the same town, the distribution of the duration of the meeting is approximately normal with mean 56 minutes and standard deviation 5.1 minutes. Let X bar 1 represent the average duration in minutes of 10 randomly selected town council meetings, and let X bar 2 represent the average duration in minutes of 10 randomly selected arts council meetings. The question is, which of the following is the best reason why the sampling distribution of X bar 1 minus X bar 2 can be modeled by a normal distribution? So remember the ways you can find normality. Either populations are normal or approximately normal, or CLT applies. Now you're told that the sample size of each one is 10, so that's not going to work, but you're also told that both populations were approximately normal. So the answer is C. The population distributions are approximately normal. You don't need to worry about CLT if that is true. Number two, consider two populations of coins, one of pennies and one of quarters. A random sample of 25 pennies was selected and the mean age of the sample was 32 years. A random sample of 35 quarters was taken and the mean age of the sample was 19 years. All right, so the mean age of the penny is 32. We have 25 pennies in the sample. The mean age of the quarters is 19. We have 35 quarters in the sample. Neither population is normally distributed, so now we have to use the other approach to find normality, which is CLT, which means both sample sizes have to be at least 30. Well, we have 35 quarters, so that's okay, but there are only 25 pennies. So the normal condition has not been met because there just aren't enough pennies in the sample. So looking at the choices, the answer is D. No, the conditions for normality have not been met because the sample size for the pennies is not large enough and no information is given about the distributions of the populations. Keep in mind that you're told the population is normally distributed or approximately normally distributed, you don't have to worry about CLT. Number three, child psychologists study the time in months that it takes for infant boys and girls to say their first words. For a certain population, the distributions of time for both populations, boys and girls, have the same mean and have the same standard deviation. Mean is 8 months, standard deviation is 1.4 months. Two independent random samples of infant boys and girls were taken, and the time it took for the infants in each sample to say their first words was recorded. The summary statistics for the number of months are shown in the following table. Riley, a child psychologist, claims that for all samples of size 40 from the population of infant boys and all samples of size 40 of the newborn girls, the mean of the sampling distribution of the difference in the sample means boys minus girls is 0.2 months. Is Riley correct? So what Riley basically did was take X bar 1, the X bar of the boys, subtract X bar of the girls to get 0.2. Is that correct? Now keep in mind when you're looking for the mean of the sampling distribution of the difference, you are going to subtract the parameter values. So you don't subtract X bar 1 minus X bar 2, you subtract mu1 minus mu2. You're told that each population mean was 8 months. So the answer is C. The mean is 0 months. In other words, if you took every possible sample of size 40 from boys and girls and found the difference, the average of all those differences would be 0. It's equal to the difference in the two population means. 8 minus 8 is 0. Don't get caught by taking the difference of X bar. That is not for sampling distributions. That would be for doing a two sample t-test for means or t-interval for difference in means. Number 4, a fair 6-sided die will be rolled 15 times and the numbers that land face up will be recorded. Let X bar represent the average of the numbers that land face up for the first 5 rolls and let X bar 2 represent the average of the numbers landing face up for the remaining 10 rolls. The mean, mu, and variance sigma squared of a single roll are 3.5 and 2.92 respectively. What is the standard deviation of the sampling distribution of the difference in sample means X bar 1 minus X bar 2? What I want you to notice is they give you this number here, 2.92. That is the variance of a single roll. It is not the standard deviation. So remember, when you're looking for the difference for the standard deviation, you are going to add the variances together and take the square root. So among these choices, which of these is correct? And the answer is C, 2.92 over 5 plus 2.92 over 10, take the square root of that sum. So you're already calculating the variance of each individual variable because you were told sigma squared is 2.92. So you can just pop those right in into the numerator of these fractions, and so you don't have to square it again. This is probably the most common wrong answer, but it's incorrect because you've already been given the variance. You weren't given the standard deviation. So in summary, this is for one sample procedures. You have sample proportion p hat, you have x bar. These are in your paper. For two sample procedures, again, this is the summary on your paper again. Now this is part of the formula sheet that you can use for the AP test. These are for proportions, so they organize it a little differently. I organized it by number of samples. So for one proportion, the sampling distribution is on the left. Now this right column here would be for doing a significance test or a confidence interval. So notice when you're doing a t-test or t-interval, you don't know what the population proportion is, so you have to use the sample proportion p hat or p1 hat, p2 hat to figure out what the standard error is. Remember, the standard error is calculated because you don't know the standard deviation of a population. So you are going to estimate the standard deviation using the standard error. So the column on the left is if you're doing sampling distribution problems. The column on the right is if you're doing two sample procedures or one sample procedures for inference. And here's the table for means. Same idea. The left side is for a sampling distribution. The right side is a standard error of a sample statistic. So if you don't know sigma for a population, you're going to use S, the sample standard deviation, or S1, S2, the sample for both samples, and those would be your standard error. That's what you would plug into your formula for procedures for means. So that's it for these extra topics. If you have any questions, you're welcome to ask me. Hopefully these don't show up, but if they do, at least you'll know what they are.